this is true for all we have geometric multiplicity equal to algebraic multiplicity. Imagine that you have eigenvalues, and for these eigenvalues the key thing is that the geometric multiplicity is equal to the algebraic multiplicity, and this is true for all eigenvalues of the matrix A. Then what will happen? The eigenvectors, okay, the eigenvectors of matrix A forms a basis for space Fn. In other words, it could be Rn or Cn actually. Okay, and we'll see that based on this result, in our next important theorem, we will prove that can be served as an algorithm to compute and diagonalize the matrices. Okay? So here's the proof of this result. Okay? So imagine the characteristic polynomial of the matrix A looks like this. Imagine there are d distinct eigenvalues of matrix A, and each one has some multiplicity. So imagine there are d distinct eigenvalues, x minus lambda 1, mu 1, power n1, x minus mu 2, power n2, so on and so forth, x minus mu d, power nd actually. Okay? So imagine that A has characteristic polynomial of this form. So what does this say? What is the meaning of, what we can interpret from this characteristic polynomial? That there are d distinct eigenvalues which are mu1, mu2, mu d, and n1, n2 and nd are the algebraic multiplicities of the eigenvalues mu1, mu2 and mu d respectively. Okay? This is what it follows. Now from this assumption, the geometric multiplicity of each, by assumption, we know that the geometric multiplicity of each of this mu I is equal to ni. By the way, I must say that the sum of these indices n1 plus n2 plus nd, this must be equal to, what do you call, it must be equal to the net n. Okay, so it must be equal to n. So the geometric multiplicity of each eigenvalue mu I is equal to the what do you call, algebraic multiplicity. But what is the geometric multiplicity? Geometric multiplicity is the dimension of the eigenspace of the matrix A associated with what do you say, eigenvalue mu I actually. Okay, eigenvalue mu I. Now, if the dimension of the eigenspace of the eigenvalue mu I is equal to ni, that means that there are ni vectors which are spanning this eigenspace actually. There are ni linearly independent vectors which are spanning, what do you call, the eigenspace mu I. So let's give them names actually. Okay. So for eigenspace, say mu1 of A, let me write it. So this is equal to say span of, okay, or let's assume that it is spanned by these linearly independent vectors actually. Let's call it u1, u2, un, or u11, u12 up to u1 n1 actually. Okay, so this first index 1 is reference. So it's with respect to the reference that these are the eigenvectors associated with mu1 actually. The independent, linearly independent eigenvectors associated with mu1. Okay, and similarly the eigenspace of mu I of A is spanned by, say, these linearly independent eigenvectors. So ui1, ui2 up to ui and I. Okay? ui and I. This is what the ui is going to be for all I equal to 1 to up to n. Okay? Or maybe if I write final one, I say that the eigenspace of mu n of A is an span of vectors u n1, u n2 up to u n and d actually. By the way, yes, this is not going to be n, but this is going to be d because there are d eigenvalues. Okay, there are d eigenvalues. Now, all these vectors are linearly independent actually. They are linearly independent. My claim is, if you put all these vectors together, okay, if you put all these vectors together, they are going to constitute a basis for what do you call Fn actually. They are going to constitute the basis for Fn. Okay, I'm writing it explicitly so that you can see actually. So I'm trying to avoid the complicated indices. So let's put, for example, let's create a matrix x1 in which the column vectors are this actually. So the column vectors are this u11, u12 and u1 and 1. Okay? And xi is u what do you say, I1, ui2 and ui and I. And last is xd. So this is going to be what? U so it's going to be ud1, ud2, d1, ud2 up to u dn. Okay? So these are the column matrices. What would be the order of each one of these matrices? Okay, what would be the order of each one of these matrices? So we're going to say that, okay, they have how many columns? So this has n1 columns, this has ni columns, this has what you call nd columns. Okay, this has nd columns. And you know how many rows? The rows are going to be n. So this, each one of the matrix has order. Okay. The order of each one of this matrix is really, let me write it precisely and carefully, n by ni. This is a matrix of order n by n1. This is a matrix of order n by nd. And now put all these matrices in a single matrix. Okay? x1, x2, up to xd actually. Okay? Put them into the single matrix. Either you can put it into a single matrix, or you can consider it as a bunch of set of vectors. Okay? By the way, what would be the order of this actually matrix? So it's going to be n by n1 plus how many columns are going to be in there? So there are n1 columns here and n2 columns here and nd columns here. So the total number of columns in this matrix are n, because it's going to be n1 plus n2 plus nd, so it's going to be n. So that's an n by n matrix actually. This is an n by n matrix. Okay? And my claim is that these matrices are the column vectors in these matrices. When you put them together, they constitute a basis of Fn. Okay? They constitute a basis of Fn. Here is an interesting observation about the matrices A. these component matrices. Okay, what would be AXI, by the way? What would be the matrix A multiplied by Xi? So you can treat this as that this is going to be that, okay, A multiplied with each one of these columns. So AI UI1, A UI2, and A, what we call UI and I. But these are the eigenvectors of the matrix A. So this is going to be mu I UI1, mu I UI2 up to mu I I and I. Okay? So this means, so if you pull out this mu I from each one of the terms, so you're going to get mu I xi. So that you can consider these xi's as the matrix of vectors which are the eigenvectors of the associated with the value mu I actually. Okay, mu I. Now, if you multiply with this identity mu I xi with the vectors yi onto both sides, okay, with the vectors yi, where yi are the elements of f and I, okay, so they are the vectors of the length and I, so that the both of these products should make sense actually. So if since you have this equality, you're going to have this equality actually. And then now, what does follows actually? Okay, what follows? What follows from here is that this mu I and xi yi, mu I and xi yi, this is an eigenpair. This is an eigenpair for matrix A associated with the eigenvalue mu I actually. Okay? Each one of, so in other words, each one of mu1 xi y1, mu1 xi y2, they all are the eigenpairs for the matrix A actually associated with the eigenvalues mu i's actually. Okay? By the way, I must say that yi belong to the f and I. Okay? So we are almost done now. We are almost done. Now we would like to show what we would like to show. We would like to show that this matrix X has a full rank actually. Okay? So the claim is that the rank of the matrix X is n. It's equal to the dimension of the entire vector space. That is the dimension of the null space of X is 0, and that is the null space of X is equal to what do you call 0 actually. Okay, 0. And if this would be the case, by the way, if the rank of the matrix is n, what does this is going to show? This is going to show that all these guys are linearly independent. Are all the vectors that are sitting inside each one of x1, x2, xd, they are linearly independent. I know they are linearly independent within themselves. Okay? They are linearly independent within themselves, but are they linearly independent? In other words, if you make a linear combination of all these vectors, the coefficients in that linear combination, are they going to be 0? Okay? The answer is yes actually. And you can show it easily by showing that the rank of this matrix X is n. In other words, all these components of the matrix X are linearly independent, and hence all these vectors are linearly independent of each other. So once you have this, so these are the n vectors which are linearly independent, so they form a basis for Fn. Okay? So they form a basis for Fn. So this is what that really we would like to show. So in order to show that rank of matrix X is n, in other words, in order to show that they are linearly independent, I need to show that the dimension of null space of X is 0. I need to show that the null space of, what do you call vector X is 0? Matrix X is 0. Now, how to do it? So in order to show the null space, let's take a vector Y, okay, from Fn. And the vector Y looks like this, y1, y2, up to yd, okay, up to yd. Now, where each one of this yi, it belongs to Fni. And let's multiply this vector Y with matrix Xn equated to 0. So when you're going to multiply this vector Y with Xn equated to 0, you're going to get what? You're going to get x1, y1 plus x2, y2 plus so on and so forth, xn, yn equal to 0. Okay? And now xd, yd equal to 0. This combination is equal to 0. My claim is each one of, if this sum is equal to 0, each one of these xi's, yi's is equal to 0. Okay? Xi's, yi's is equal to 0. What if they are not equal to 0? Okay, why they are equal? So why this xi, yi must be equal to 0? Okay? Keep in view that these xi's are these eigenvectors actually, associated with eigenvalues. Now from the result, previous result, the result that we did in our last discussion, that that if you have distinct eigenvalues for a matrix, then the corresponding eigenvectors, okay, they must be linearly independent of each other. They can't be linearly dependent. Now, if xi, yi is not equal to 0, that means that you are assuming that corresponding to the distinct eigenvalues, okay, you have eigenvectors which are linearly dependent actually. So this would be a contradiction. This would be a straight contradiction actually. So each one of the summand has to be 0 actually. Okay? And if each one of the summand has to be 0, what does this is going to imply? This is going to imply that yi equal to 0. Okay, the yi is equal to 0 because xi's are not 0, so yi must be what do we call 0. And if each one of the yi is 0, this means that y is 0. So we considered y from the null space of x, and it turns out to be 0, so this is the null space of x is 0. And if the null space of x is 0, rank of the matrix x is n. And if the rank of the matrix x is n, all these vectors are the vectors in these matrices, they all are linearly independent actually. And how many vectors are there in this vectors? How many column vectors are there? There are n column vectors. In other words, put all these vectors together, okay? So the total is going to be the n column vectors, and all these n column vectors are linearly independent. So if they are linearly independent, they constitute a basis for Fn actually. Okay, they constitute a basis for Fn. So what does the net conclusion of this result? If you have a strange kind of a matrix in which all the eigenvalues have the same algebraic multiplicity and geometric multiplicity, then the eigenvectors associated with the matrix would constitute a basis actually. Okay? Now we are in finally position to prove our major and basic criterion to diagonalize the matrices actually. Okay? To diagonalize the matrices. We haven't yet defined that what do you mean by the diagonalization of a matrix? We're going to define it soon, but after proving this important theorem actually. Okay? After this theorem. So this theorem says that let A be a square matrix with entries from F, then Fn consists of bases of the Fn maybe has a basis, okay, consisting of eigenvectors of A if and only if A is similar to a diagonal matrix, similar to a diagonal matrix D. That is, there exists a matrix P such that P inverse D, that is a diagonal matrix, P is equal to what you call A actually. Okay? What do you call A? So this is what that we have to prove. So this result says that every matrix, and basically we're going to define later what do you mean by diagonalizing a matrix by saying that A matrix is diagonalizable. I'm saying that A is similar to a diagonal matrix. That's what really the definition of diagonalization of a matrix actually. So a matrix is diagonalizable if its eigenvectors comprises or construct a basis for Fn. So this is what the theorem is saying actually, that if for a matrix eigenvectors comprises a basis of Fn, then A is similar to a diagonal matrix. In other words, A is diagonalizable actually. Okay? A is diagonalizable. Here's a proof. So let S1, S2, Sn be the eigenvectors, okay, corresponding to the eigenvalues lambda 1, lambda 2, lambda n, such that they form, in other words, these vectors form a basis for Fn. Okay, they form a basis for Fn. Question: can we find a matrix P and the diagonal matrix D, okay, such that this is true? Okay, such that this is true. The answer is yes, actually. You can easily find it. It's not difficult. So take matrix D as the diagonal matrix in which on diagonal entries you put the eigenvalues. This is 0, this is 0. Okay? And take the matrix P in which you take these eigenvectors and put them in columns S1, S2 up to Sn. My claim is that if you compute the P inverse dP, multiply them, you're going to recover what do you call A actually. R, so if A is PD B inverse, then A is equal to, AP is equal to PD. So this is what that you need to show. So if I show this, I have shown this actually. So I have a choice for D and a P. So let's compute AP. So when you're going to compute AP, what you're going to get? So this is going to be AS1, AS2 up to ASN actually. Okay? Now what is AS1? AS1 is S1 is the eigenvector associated with lambda 1. So this is going to be lambda 1 S1, lambda 2 S2, and lambda n as n active. Okay, this is what that you're gonna get, and you can write this vector explicitly as that this is